Today we will be discussing about the real life problems of the composite materials, and we'll try to understand what are these real life problems in the related to composite materials, and how to solve these particular problems. So we know that composite materials are nothing but a combination of matrix and the reinforcement, and its mechanical properties are superior compared to any one of these, right, either matrix or reinforcement. So majority of you might be aware that maybe aware of this laminated composite, right? So multiple layers of fabrics stacked together and impregnated with the resin material, right, and cured using let's say, for example, at the room temperature or maybe at certain temperature using the compression molding technique or vacuum bagging technique, right? You must be aware about this various composite manufacturing techniques, right? So let me show you some this fabric preforms. I have specifically prepared this for this particular session. So this is the glass fabric, right? And we can produce the glass laminate, that is laminated composites. So for example, we can stack the fabrics one above the or other, right? And we can have multiple number of layers depending upon the required thickness, right? So for example, let's say the one layer thickness is, let's say, 0.1 mm or 0.2 mm. Generally it is 0.1 mm. So depending upon the required thickness, for 600 tex yarn you will get 0.1 mm thickness, right? Thicker the yarn, the fabric will be thicker, right? Or you can arrange these particular layers at certain angle also, right? For example, let's say this is the 0-0 arrangement. For example, this is 0-90 arrangement. So you can have some layers at 45 degree or some other angle, maybe depending upon the properties required. So you must be aware that this composite is designed. For example, this laminated composite. So this is the carbon fabric. This is the 12K carbon yarn fabric. And here also you can produce laminates based on your requirement, right? According to the, you can arrange these layers at different angle based on the properties required in that particular direction. Because एक चीज यहाँ पर important है that textile materials are anisotropic in nature. You know that, right? You have some properties in 0 and 90 degree, and at bias angle you will be having different properties. So ये anisotropic है, and our composite material, that is textile reinforced composite material, is also anisotropic. So we will start with the what is the main problem during in the composite material. One of the major problem is the voids. You may be aware about the voids.
Porosity.
Yes, void means air gap. Right. So it is ideally in the composite material we know that matrix is the continuous phase, right, and reinforcement is the discontinuous phase. So when we are producing, let's say this is the one of the composite material. Let's say this is the composite material we have produced. So in this composite material, the matrix should be continuous inside this particular composite structure. But actually it doesn't happen. Ideally it should be continuous, but actually because of the limitations associated with our techniques. For example, we are using, let's say, hand layup technique. In hand layup technique, what we do, we simply take the reinforcement, right? For example, अगर ये plain woven कपड़ा है या कोई भी, this is the twill woven carbon fabric. So what we do, simply let's say 4 layer का कपड़ा अपने को, for example, we have to make a composite with 4 layers. So what we are doing is, we are taking one layer, applying a resin, epoxy resin, for example, by hand, then putting a second layer on it, again applying the epoxy resin, third layer, fourth layer, like that. And we are applying some dead weight on it. Suppose you are curing at room temperature, then we simply keep it like this only for maybe around 24 hours. Generally resin is cured at 24 hours.
तो epoxy resin might be inflammable ना, जल जाता होगा?
नहीं
epoxy जलता है?
Epoxy resin is not flammable. So you can cure it at higher temperature also. मतलब for example at 120 degrees for around 20 minutes. Epoxy resins comes in various grades depending upon the composite manufacturing technology. For example, if you are manufacturing, let's say, and also depends upon the type of application. For example, the aerospace grade epoxy resins are different. For example, you have some automotive composites. For automotive application, the epoxy resin grades will be different. For some other applications, it will be different. And depending upon the technology also. For example, you are producing filament wound composite materials. In that case, the epoxy resin grade will be different, where the pot life is higher. You know pot life of the resin, pata hai aapko? So let me tell you what is pot life. So we will have one more session on the development of composite material, hands-on experience. So in that also we will discuss it in detail. Pot life means what? When we are mixing resin and hardener together in a desired proportion. For how long this particular resin is the curing is not started. Resin is in the you can say it is in a flow. It is in a flow, and you can apply it without any problem. So that particular time, at how much time any resin hardener reaction starts. So that particular time we call it as a pot life. And in case of filament winding, suppose you know filament winding process. पता है आपको filament winding? Yes. So in the filament winding, you know the winding of the filament it takes long time, and therefore in that case the resin required is different grade. So it has a higher, longer pot life. So in case of compression molding, we use resin which is having shorter pot life, maybe 20 minutes, 30 minutes, maybe maximum 1 hour, right? For example, vacuum bagging, again you can have a resin with longer pot life when you are having a larger component. For example, windmill blade you are manufacturing. So is a longer part, for example around 40 feet, 35 feet longer part. So in that case again you should have a longer pot life. But small parts you can have a resin with small short pot life. So what happens is that because of this, if you look at the different composite manufacturing techniques, let's say it is a hand lathe or it is a compression molding technique, where you are curing at elevated temperature, so that your curing time is reduced and you can produce multiple components within small time. Or let's say vacuum bagging technique. So you see that since the technique is different, what happens is that the properties of composites are also different, right? And one of the reason is the voids. One of the reason is the void. Void is nothing but a air gap in the composite material, right? And that air gap actually causes stress concentration when that particular composite material, let's say this is the composite material having voids in this particular composite material, let's say. So what will happen under the loading, let's say any type of load, tensile load or bending load or impact type of load, because of that void, that particular area becomes an area of stress concentration, and from where actually your failure start. For example, this is the one sandwich composite material, and let's say this is the sandwich and you are using it in the flooring. So you must be aware that in the floorings of, for example, aeroplane, for example, your superstructure of ships, right? So where in the flooring we use honeycomb type of composite materials, right? Because they are high energy absorbing composite materials. And let's say if there is a void in these particular structures at any place, so what will happen? From there actually your failure start first. That particular point becomes a stress concentration point. And why it becomes a stress concentration point? for this you must be aware of, or you must be knowing the composite failure mechanism, right? आप सभी को पता है composite failure mechanism. So what happens is that whenever load is applied on the composite material, that load may be tensile, compressive load or bending load. Matrix material, the continuous phase first takes the load, and it is distributed right throughout the structure, and it is transferred to the reinforcement. And how much strong your matrix and reinforcement interface, that decides how efficiently your matrix will transfer the load to the reinforcement. And if there is any void, so void is again a defect, so that particular void will become a stress concentration point, and from where your composite will start fail or deform, right? So this is the one of the common problem in the composite material, that is void, and how to avoid these particular voids. So one of the way is to use vacuum bagging technique, right? So vacuum bagging, आप लोगों को पता है vacuum bagging technique और vacuum assisted resin infusion technique? आज ही पढ़ा है, okay. So we have actually ordered that particular setup, so that's why we are currently not having. Maybe in the next week we will be having this particular setup with us. So why we are using this vacuum bagging technique? If you see the composites used for automotive components, or you say the windmill blade or aerospace component, जो भी windmill है वहाँ पे wind का blade है या windmill का blade है. So there we are using vacuum bagging technique. Why? Because of that particular technique you can remove the voids to the greater extent, but you cannot get composite with 100% free of void. There will be certain voids because of the and then that depends upon the how much is the dimensions of the composite, how dimensions, as well as what type of reinforcement you are having in that particular composite material, whether it is in the fiber form or whether is it in the fabric form. But fabrics are of different types. For example, whether is it a oven fabric or whether it is a randomly oriented glass mat, or whether it is a 3D fabric, right? So based on that also the void content will vary even you produce the composite with the vacuum bagging technique. But again, in comparison to your other techniques, for example compression molding, you will get lesser voids in case of your vacuum bagging technique. So the next problem is so let me tell you the next problem associated with the composite materials. So is there any doubt in this particular discussion? और आपके पास कोई भी क्वेरी भी है वो भी आप बीच में पूछ सकते हैं, मुझे रोक के कोई प्रॉब्लम नहीं, सो दैट ये सेशन थोड़ा सा इंटरेक्टिव हो जाएगा, राइट? तो दूसरा प्रॉब्लम है हमारे कंपोजिट मटेरियल के साथ, वो है डीलैमिनेशन का. आप सभी लोगों को पता होगा डीलैमिनेशन, आप सभी लोगों ने पढ़ा भी होगा और एक्सपेरिमेंट भी किया होगा, आपने देखा होगा. सो लेट्स से सपोज दिस इज द कंपोजिट मटेरियल आई एम हैविंग, राइट? सो इफ यू लुक एट दिस पर्टिकुलर कंपोजिट मटेरियल, ये आपको बहुत ही अच्छा दिख रहा है यहाँ पर, लेकिन जब हम इसका टेंसाइल टेस्टिंग कर रहे हैं या इम्पैक्ट टेस्टिंग कर रहे हैं या बेंडिंग कर रहे हैं, व्हाट इज हैपनिंग इज दैट डीलैमिनेट हो रहा है, क्योंकि ये लैमिनेटेड कंपोजिट है वेयर वी हैव स्टैक्ड टुगेदर अराउंड 6-7 लेयर्स, right? And you see that this is the composite failed under tensile loading. You see the delamination. Why this delamination occurs? Because simply the ये जो सारे reinforcement के layers है, they are stick together because of the matrix material, right? Because of the matrix material only, and definitely under loading the what will happen is that if efficiently you are even though your stress is transferred from the matrix to the reinforcement efficiently, the individual layers will carry load individually, right? And how much is the distance? If you look at the center of the moment of inertia effect will be there, that you are applying load like this on this particular material, but from this center, the layers which are away from this particular center will take load differently. The layers which are at the center will take load differently, and that is the reason why this delamination. That is one of the reasons why delamination occurs, because your individual layers are taking load differently. So how to then mitigate this particular problem of the composite material? So and you see that one more important thing is that majority of the composite materials today produced are laminate composite. You take example of the composite materials used in aerospace, or maybe in the ship, or maybe in the your this windmill blade, or for example automotive components. So they are or the railway components. In the railways also a lot of composite materials are used today, and this delamination problem occurs, especially in case of any type of load. So how to mitigate this particular problem? So for this particular problem, to solve this particular problem, I would like to show you one. So this problem can be solved using this 3D fabrics. Do you know about 3D fabrics? 3D fabrics के बारे में आपको पता है कुछ? No sir. ठीक है, मैं बता देता हूँ. So let me show you. So 3D fabrics क्या होता है? 3D fabrics are the fabrics having, the normal fabrics has length and width. It has also thickness, right? But the thickness of this particular normal 2D fabric is maximum 2 times the yarn thickness, because you have yarn in X direction, Y direction, and this thickness will be maximum 2 times the yarn thickness. But why we call this particular fabric as 3D? Because it has length dimension, width dimension, as well as thickness dimension, and thickness dimension is multiple times than the multiple times of your yarn thickness. So yarn, you understand, yarn means धागा, right? जो धागा है उसको हम yarn कहते हैं. So in this
minimum thickness means double the width of the yarn.
Yes.
That's a minimum or a maximum?
Yeah, maximum. Right.
Maximum. 2 times.
So maximum thickness will be 2 times your yarn thickness in this case. But in case of your 3D fabrics, you see that your thickness will be multiple times of your yarn thickness, and you can produce 3D fabrics of desired thickness depending upon जो भी आपका required thickness है for particular application. We know that if you want to produce laminated composite out of this simple single layer, normal 2D fabric. So if you want to produce, let's say 1 centimeter thickness, so based on what is the thickness of your single layer, you have to take a number of layers of this particular thing. In case of 3D fabric, what you can do is, here also if you want to have, let's say 1 centimeter thickness, so you can take number of layers. You can take number of layers and you can produce the 3D fabrics. 3D fabrics, the classification of 3D, if you look at the 3D fabrics itself is a very huge, you can say, group of material, a very huge group of materials. And in 3D fabrics, these are the 3D solid structures. This is the 3D solid structure, and let me show you that in this 3D solid structure, so we can have 3 different type of 3D solid structures. So you have this 3D orthogonal structure. 3D orthogonal का मतलब है कि all the layers, all the 3 sets of yarns in this particular fabric are perpendicular to each other. Orthogonal means perpendicular to each other, right? 90 degree. So you have 3 sets of yarn. For example, you see in this particular fabric, you have 2 sets of yarn. One set is vertical sets of yarn and another is horizontal set of yarn, right? Only 2 sets of yarns. But here in case of 3D fabric, you have 3 sets. One is vertical, another is horizontal, and the third one is the through the thickness, which is binding these layers together. So one is horizontal, one is vertical, and the third one, which is a binder, binding these multiple layers together.
So it's not one and one, it's actually multiple in horizontal and vertical, and they are binded by the
binder, right? So you have, but again, one more thing. So this is the one type of a 3D solid structure, that is 3D orthogonal. You can have angle interlock structure where the binder yarn, so here in orthogonal your binder yarn is 90 degree. Means all the yarns in this particular structure are 90 degree. And particularly this classification is, if you look at this, so you will see that the binder is making 90 degree here also. In case of angle interlock, your binder is going through the structure at certain angle. So that's why we call it as a angle interlock structure. And third is the layer to layer interlock. So where the different layers are interlaced with each other, right? So they are attached to each other, and this is integral structure, integrated structure, integrally woven structure, means you cannot separate these layers. So if you make a composite out of this particular structure, composite reinforced with this particular structure, it will be, since it is an integrally woven structure, so there will be no delamination at all in this particular structure. There will be no delamination. So when you apply any type of load, maybe tensile, impact or bending load, it will not delaminate.
White may also be reduced in this form.
No, this is again questionable, because why? If you look at the structure, how the structure is developed, that is very much is how you are designing that particular structure is crucial in this particular case. In case of your laminates also, let's say this is the twill woven structure. It is a twill view. You can have another structure, that is this is the structure we have developed. This is the hybrid structure. This is jute and jute glass hybrid structure. This is the plain view structure. Now the thickness of the structure that you get in different views is different. The another thing is that if you are producing, let's say, composite using vacuum bagging technique, or let's say a compression molding technique, so what will happen, you must be aware about the resin rich areas in the composite. आपको पता है resin rich area. So composite material, let's say मैंने composite material बनाया for example, ठीक है. So what happens is that what I ideally expect is that at every place, let's say मैंने यहाँ पे 5 mm by 5 mm कट किया है यहाँ पे हर एक जगह पे. At every place the fiber volume fraction should be uniform, right, throughout the composite. But what happens is that if I am changing the view structure, my and let's say I am using let's say same fabric I am using in compression molding, same fabric I am using in vacuum bagging and producing same composite material, right, with same fiber volume fraction. But since your view structure is different, it will lead to variation in the fiber volume fraction at the micro level. So at some places where you are having the floats, it may lead to the formation of the resin rich areas. So here also, in this case also, in this 3D fabric also, so in case of this orthogonal structure especially, here in between the layers you will get a resin rich areas. They are micro areas, dimensions less than around 1 mm or less than 1 mm dimension, but still you will get some at the micro level variation in the fiber volume fraction, and this resin rich areas again are stress concentration areas. This because you must be aware, once you understand the mechanics of the composite material under loading, you can understand the problem of the resin rich area, that it will be a stress concentration point and where the failure will start, right?
So also kind of defects.
Yes, we should have uniform fiber volume fraction throughout the composite structure, but certain faults we cannot avoid, right? Certain things we can avoid, but we cannot avoid all the problems. There will be certain problems and we have to work with that, and we have to develop a composite with we can say a desired factor of safety, so that that particular structure will work in real life. For example, your windmill blade, for example, your automotive components, or for example, the wing of the aeroplane. So you look at this particular structure. This is the 3D oven, orthogonal oven jute fabric, right? Here is your plain oven fabric. Here is your plain oven fabric, single layer plain oven fabric, right? And this is the 3D orthogonally woven fabric structure. So in this particular structure, let's say this is the for example, let's say 8 or 9 mm thickness, for example, you have, and to produce this much thickness, I need to use multiple layers of this material. But if you look at this, since this is the integrally woven structure, the failure modes will be different. It will be a maximum load compared to your laminate, and since the failure mode is different, so the life of the composite material in this case it will be more than your laminated composite.
Is the inner house prepared? Or
Yes, this is inner house prepared. Yes. So we have the setup here and we prepared by our own. If you look at the national level and international level, manufacturing this 3D fabric, you do not have any commercial look. Only in 1 or 2 industries they are commercially manufacturing these 3D fabrics. So we are again fabricating one 3D weaving machine here. We have DST funded projects. So in that we are fabricating 3D weaving machine, which will be of commercial scale. So this is the one of the problem. It is the delamination problem. The second thing I would like to show you. So in case of this is the sandwich structure, right? So this sandwich structure is again a composite sandwich structure, and you know the sandwich structures are used for multiple applications, right? Specifically for energy absorption के लिए हम इसको use करते हैं at various applications. And this particular sandwich structure, if you look at here, what we have done is, what is done here is that different layers are sticked together, right? First, you have this corrugated layer, so you can have a corrugation of any dimension, any shape based on your requirement. So you can have triangular shape, right? You can have rectangle, or you can have hexagon, right? And what is done is that after making this corrugated structure, it is stacked together to according to the desired thickness, how much thickness you need. So based on that, it is stacked together and simply it is sticked by resin. So this type of, again, this is the one of the good composite material, good sandwich composite material, which can also bear good amount of load. But what is the problem again associated with this particular composite? Delamination again, because it is sticked only with the help of your epoxy resin. तो ये क्या होगा, जब आप इसके ऊपर कोई भी लोड आएगा, चाहे वो फ्लेक्चुरल लोड हो या इम्पैक्ट लोड हो या टेंसाइल, तो नॉट, बिकॉज उसका एप्लीकेशन अलग है जहाँ पे फ्लेक्चुरल और इम्पैक्ट लोड ही आएगा या कॉम्प्रेसिव लोड आएगा. So एफिशिएंट एनर्जी ट्रांसफर तभी होगा जब यहाँ पर you can say the bonding between these layers is proper, and since it is sticked by the matrix material, so it will not bear the load, as much load as compared to your integrally woven preforms. So let me show you the integrally woven preforms. So you look at these particular structures. Look at this particular structure. These are the hollow structures, and these are integrally woven structures. जब आप उसको weaving machine पे बनाते हैं तो ये ऐसे बन के आता है ये कपड़ा सीधा. Whereas in this case you see that ये तो चिपका हुआ है. It is sticked by using the epoxy matrix or any other binder. But here, this particular fabrics, if you look at, these are integrally woven structures. You can weave these structures and you can produce different shapes. And we have prepared it already, and we have produced these particular structures. And we can have different cross-sectional shapes. You can have triangular profile, we can have trapezoidal profile, rectangular, or any other profile. Any other means the shape we can have here. And what is the advantage of this integrally woven structure? Again, the load transfer will be more efficient. So there will be no delamination. And to produce this structure, you need a strong knowledge of the weaving technology, of fabric manufacturing technology. And these structures are also nobody produces in India, right? So you look at this particular. This is the honeycomb structure, hexagon. You can get. So we have again produced this particular structure using weaving technology. And you can get directly on the weaving machine itself, you will get a fabric like this, and you simply have to insert the mold into this particular hollow channels, and using vacuum bagging technique we can produce the composite material. So let me show you one more thing here.
This technology or this machinery is available with the department?
It is not available here. I have produced it in IIT Delhi, so IIT Delhi. But here I am, as I said you that I am developing one 3D weaving machine here, where we will be able to produce 3D fabrics with different thickness. We can produce 3D fabrics with this type of spacer structures and the composite materials. So this is the spacer fabric, and this is the composite material of this particular spacer fabric. So the weaving technology is. Let me show you one more important thing. So you know this profile weaving, profile structures. So this is again. Let me show you why we use these profile structures. You see this particular structure. So ये भी structure जो है ये हम जब weaving machine पे बनाते हैं तो उसी shape में आता है. You can produce structure of any shape. So this is the profile, pie profile. So we have produced it by our own hand on handloom. So why these profile structures are produced? If you look at aerospace composites, if you look at the automotive composites or any other composite material where you need to join the composite components, right? So in that case, what is generally done is, for composite joining, what is done is, we can have riveting or we can fastener, you can use fastener also, there is no problem. But what happens is that the junction, this is the junction, right, where this ये जो surface है and this part is joined together right, using this particular material here, and here you have fastener. Now what happens is that, let's say you have a composite material and you want to join this composite material. So you can use a fastener, there is no problem. So let's say for example this is the T profile, and let's say I want to join some component here and some component here, we can use the fastener, there is no problem. But what happens is that the problem occurs at this particular junction. How much is the load taken by the junction, and there actually this particular composite material this particular joints fails, right? Because junction is the stress concentration point in this particular type of you can say joints. So if you look at this particular, so this is how this particular profile structures view. Actually, if I explain it, it will be difficult for you to understand because your background is completely different, I can understand. But let me tell you that this is a special technique to produce such type of profiles, right? So where we have produced by our own hand different type of profiles. U profile, plus profile, L profile, blade profile, you can have, and their composites. And we have also produced the profiles by stitching also. So this is the integrally woven profile, this is the stitched profile, this is the integrally woven U profile, this is the stitched profile, where this 1, 2, 3 fabrics are stitched together here. This is the stitched blade profile, this is integrally woven, this is again integrally woven, this is stitched profile. And composites of these all are produced. And we have tested it for the junction strength. What will happen to the composite at the junction? You look at this, for the stitched composite, the composite fails only at the stitch line, because there only it is the different layers are held together by the stitching only, the stitching thread only. But if you have the integrally woven structure, it will fail due to the fracture of the yarns. And this particular integrally woven structure will bear more load, much more load at the junction than your stitched profile. And this technique is again, let me tell you that this is again a very special technique, and for this again you need a in-depth information or knowledge about the weaving technology. And these preforms are also not available commercially in India, but they are available in some other countries. And we are in India, we are trying to develop these structures also, profile structures. So one of my PhD students, he will be working on these particular profile structures, but we have developed another technique for producing these particular profiles and their composite materials. If you are interested, you please register for that particular course, specifically for the 3D fabrics. So this is the one that is the delamination, and I have shown you, if you change simply the preform structure, you can avoid certain problems, you can get enhanced mechanical performance, desired mechanical performance. Third problem है हमारे composite materials में, वो है that is the health monitoring of the composite materials. Suppose for example you have a composite material, let's say windmill blade you have, right? 40 feet का windmill blade है यहाँ पर और वो rotate कर रहा है, let's say for last 1 year, and you don't know that इस windmill blade में हो या आप एरोप्लेन का ब्लेड हो या कोई भी दूसरा ऑटोमोटिव कंपोजिट है या let's say सुपर स्ट्रक्चर जो शिप है, शिप का जो सुपर स्ट्रक्चर है वहाँ पर ऑफ दिस पर्टिकुलर कंपोजिट मटेरियल, you can understand, you can observe the you can say the damage that is happening at the surface, but what is happening at the inside of this particular structure we cannot get. And we has been already reported many of the failures of the such composite material, catastrophic failure of the composite material, because of non-detection of this particular defects in the composite material. So for example, defects क्या हो सकते हैं यहाँ पर? Micro cracks. So for example, let's say this is the jute epoxy composite material. Or maybe you have glass epoxy composite material, or you have carbon epoxy composite material, and it is used in the let's say aeroplane wing, right? Or you have this. So for example, this is the strain monitoring sensors. So we have glass fabric as a substrate, and on this particular glass fabric we have developed one recipe using this graphene based materials. And since we know the graphene is conductive, graphene based materials are conductive in nature, so this particular material will become a sensor, and we embed this particular sensor in the composite materials and try to measure the change in the resistance under the deformation. So we expose this particular material occur, and that we are trying to correlate that particular change in the resistance with the deformation in the particular composite material, and try to develop a sensor which can be calibrated, type of a sensor which can be calibrated and which can be used in composite structures, a huge composite structures. For example, you have, let's say, windmill blade ho, yeah, for example, unmanned air vehicles which are specifically used for surveillance purpose, right? For example, you have again various aeroplane. Of course, yes, absolutely right. होना चाहिए. Composite at the outer layer or at the edges, again on the top side as well as at the edges also. So it is different. If you look at the composition, it is from the composition point of view, it is different. This is not like a normal glass. But if you see the composition wise, definitely if you look at the chemistry of the fibers, or if you look at the requirement of any polymer to produce a fiber, so there are certain requirements. So otherwise we cannot produce filaments or textile fibers from any polymer. Okay, so 3D printing, 3D viewing are completely different. So they are completely different. So relating 3D viewing and 3D printing is, from my point of view, it is completely we cannot relate.
But sir, आजकल 3D printing में continuous fiber 3D printing भी आ रहा है.
Yes, continuous fiber. Your question is very right. We can use textile-based fiber, right, filament, and we can imprint it with the matrix, and we can put in any shape, right? But that is different. That the technique is different. What is the problem with that particular technique? Is, let me tell you. If you look at the structure, that structure is not interlaced type of structure. In case of weaving, it is an interlacement. It is interlacement of yarns. So the structure is different. And in case of 3D weaving, you see that it is an integrally woven structure. It is a one structure, entirely one structure, and there is no stitching or something like that. In case of 3D printing, you are simply laying the filament impregnated with the matrix in different shape. But if you look at the deformation behavior of this particular composite material, let's say 3D woven composite and 3D printing, it will be completely different. So because you know that if you, that's why I'm saying you that agar aapko deformation behavior, or in the other words मैं बताऊंगा, if you understand the mechanics of the composite material under different loading conditions, you can easily understand which composite material will give you more mechanical performance. So that for that particular thing, you should understand how your composite will be deformed under various loading conditions.
A study is published in e-glass fiber for DLP assisted printing. And they are increasing the mechanical strengths.
But we have to compare. We should compare what is happening. Look, what happens is that study of the composite material is one thing, and when we are looking at the application point of view, when we are trying to implement in a real application, for example, let it be any, let's say, aerospace component or maybe windmill blade, how that component is behaving in that particular conditions, and how it is failing in that particular condition, how it is taking the load, how long it will be, it can be used for that particular application. I mean, the life of the composite material. We have to look at these particular things. So एक चीज मेरे को बताना है आपको, that is the last again one point, that is the problem the problem of the composite material, that is the effect of environmental conditions. For example, let's say temperature, or let's say the moisture, or maybe the UV, right? So that is again if you look at the
कुछ और रिएक्ट करती हैं, और अगर हायर टेम्परेचर जैसे समर्स में ज़्यादा डिफरेंट बिहेव करने लगती हैं, तो उनकी ये भी टेस्टिंग सर चेक की जाती है?
Yes, we can do it, because you know, when you are using these composite materials, when you, for example, you are using in the windmill blade, so you know that aeroplane generally flies at the height of 35,000 feet, where the temperature is in the minus 50 degree, minus 40 about it. So in that case, in that particular conditions, your composite should be composite should sustain that particular environmental conditions, right? So definitely we have to test it. If you, for example, the satellites, many satellite components are the composite materials. So when they are going in the space, so again the environment is completely different. So for that you have to do the test according to that particular environment, so that that component will sustain in that environment. Definitely we have to do that. For example, your composite is used in the ship, superstructure of ship, where the environment is different. Your composite may experience humidity. Your composite experience the seawater, right? Salts. So the composite, again you have to test for that particular environment, so that it will sustain in the real life application.
So in the 3D fabric that you showed, I think the binder is the main component that prevents the delamination of the layers. And in the normal composite, the bonding strength between the matrix and the reinforcement, that is the that prevents the delamination. So can the single binder can withstand that much of shear load that causes the delamination, or the matrix, the resin that we use, that also has some load?
Okay, good question. So for that you have to observe this 3D fabric. If you look at it, it is not like only one binder. It is not only one binder. There are multiple binders across the width of the fabric. Across the width of the fabric. And if you look at the different layers in this particular structure, you will understand that the horizontal layers and vertical layers, they are like this. Right? They are like this. And the binder is again binding these particular layers together. So it is not the one binder, right? So in that particular diagram, it was the unit cell of that particular structure where only one binder was shown. But if you look at the structure throughout the width, we can have multiple number of binders, and based on number of binders, we have already done one study that when you change the number of binders, the impact energy absorption of the composite material changes. Right? More the number of binders, the impact energy absorption will be more. And one more thing is that in case of this orthogonal structure, the stiffness of this orthogonal structure is very much high compared to your angle interlock and warp interlock structure. So for example, if you want to produce a composite material where the shape is, let's say, a curvy shape, for example. So in that particular shapes, you should not use 3D over orthogonal structure. You should use angle interlock structure or warp interlock structure, which is more flexible compared to your orthogonal structure, and which will give you more flexibility during the manufacturing of the composite material. Right? If you look at this particular structure, it is highly stiff.
Yes.
So if I want to produce a curved shapes, it is very difficult. Right? But if I use this angle interlock structure or warp interlock structure, they are more flexible, and you can use it in a for such complicated shapes or maybe some curves. Right? So any other doubt we can discuss. We have produced here
Orthogonal.
orthogonal structure, 3D over orthogonal using jute yarn. This is the jute yarn.
So, yeah, just I'm curious to ask, we have carbon composites, we have multiple directions we use it in that. So is there that provision, can we customize this kind of a weaving where we can have multiple directional weave which is possible? So now it is a 3-directional weave. So like there is like fourth direction or a 5th direction which will come is other than the 3rd directions, which is
There is a confusion. 3-dimensional fabric doesn't mean yarns in 3 directions. 3 dimensions means it has 3 dimensions: length dimension, width dimension, and thickness dimension. In case of, I got your point. In case of, you mean to say that can we have yarns reinforcement in multiple directions, any other direction, and it is an integrally woven structure at the same time? Is it that? So we can have this particular structure, and these structures are commercially produced, where multiple layers of yarns in, let's say, 0 direction, multiple layers in the 90 direction, multiple layers at bias angle, let's say 45 angle, they are laid and they are stitched together using needles, and these structures are commercially produced. They are in the production and they are used in variety of applications, and windmill blade is one of that.
Sir, what type of testing generally we followed in the textile? Generally, for example, in the mechanical materials testing and non-destructive testing or some destructive testing are followed, ultrasonic testing, vibration testing. In the textile, which type of testing is?
For textile materials or composite materials?
For composite materials,
Achha.
which type of testing?
For the composite material, again, we can have tensile testing, 3-point bending or 4-point bending test, compression test. If you have such sandwich composites, we can have a compression test. Again, for the sandwich, we can perform the bending test, impact test. So for such laminated composite or 3D fabric reinforced composites, we can have impact test. For example, you can have Charpy impact or Izod impact. So this is the in-plane impact test, Charpy and Izod. You can have out-of-plane impact test also, that is drop weight impact. So you can have a drop weight impact. Again, you can have a static or you can have a dynamic impact test.
Is there any non-destructive type testing is here like ultrasonic testing, vibration testing?
No, it is not there. It is in.
So that we can recognize the internal cracks and voids.
Right. So for that you have to do the micro-CT scanning. Micro-CT scanning is one of the non-destructive tests performed to understand the internal structure of the composite material. Let's say after testing also you can find out what has happened in the internal structure, or before also to identify the voids. And micro-CT scanners are widely used, and they are available in India. It is available in ILD also. It is available. Micro-CT scanning is one of the non-destructive tests we carry out, and generally for all these aerospace components, micro-CT scanning is done to identify any void in the structure.